Hello. Today we're going to talk about a numerical method that's called Euler's method. And this numerical method is using an approximation method. The idea here is that maybe we're not able to come up with an exact value for a solution to a differential equation. So Euler's method is going to use the differential equation as a foundation for building this algorithm that gives us an approximation of some unknown solution. What we're going to be after, though, is coming up with the value, like a number, not just a function. And it's going to require us to know some information about our differential equation. In particular, we need to know what the differential equation is, but we also need to know one point, just one point that the solution could possibly go through. And typically that's the initial value, okay? So this is what we're talking about right here. To implement Euler's method, we need a differential equation, y prime, written as some function of f of x, y. And then we need the initial values, y of x naught is equal to y naught. And we're going to use those in order to build up our approximation function. Now, the linearization function that we learn about in Calculus 1, I believe, was called L of x, and it was written as y naught is equal to, L of x is equal to y naught plus f of x naught y naught times x minus x naught. And the idea here, like where this came from, is if we kind of work backwards from this, and we remember that L of x is just some other y value, then if I rewrite it as y equals y naught plus f of x naught y naught times x minus x naught, and then I subtract the y naught and divide both sides by the x minus x naught, then we get y minus y naught over x minus x naught is equal to f of x naught y naught. And f of x naught y naught is simply the y prime function. But it's, y prime, or in this, I guess it's y prime evaluated at x naught y naught. Okay? And we know that y prime is a slope function. We know that y minus y naught over x minus x naught, that's a change in y over change in x. That's the slope value of something. So this whole premise is based upon the idea of knowing the slope of a straight line, okay? So that's why we call L of x a linearization function. It is literally a line-making function, okay? It runs tangent to the solution curve at the initial value. And so the point in question here, we're talking about at x naught, y naught, okay? And then we're going to let h be some small positive increment on the x-axis. And we're going to kind of reconstruct our linearization function to fit our needs in this course, okay? So h is some small value on the x-axis, and we're going to replace the x that is in x minus x naught by x1 is equal to x naught plus h. So that's saying that the first x value will be replaced by x naught plus h in L of x. And if we think of that along an x-axis, if this was x naught, and this next value is x1, then the difference between x naught and x1 is just some small value h. Okay, so that's where that's coming from. And so if we do all those replacements, then what we get here is the linearization function evaluated at x1 is equal to y naught plus the derivative function, the dy dx function, f, evaluated at x naught, y naught, times x naught plus h, so that's replacing our x value, minus x naught. Okay, well, I see in here we've got an x naught minus an x naught, so those are going to go away and just leave behind an h. So our formal equation, if we know x naught and y naught, we can now evaluate the linearization function at the next x value, x1. And then we would say that the linearization function at x1 is simply equal to the y naught value plus h times f of x naught y naught. Okay? Now, if we define L of x1 to be our y1 value, then we get this sort of notation right here. Okay, y of x1, so the actual y value, the actual solution evaluated at x1 is going to be approximately this y1 value that we get. And this y1 value will be equal to the linearization function. So here's what I'm saying on this, okay? I've got this picture right here, and we've got a curve, the solution curve in blue, and we have a tangent line in red. This point right here, I've highlighted it, this is where x naught, y naught is, okay? And we don't actually know the solution curve, but in order to talk about this, we have to look at a pretend solution curve, okay? And now, the idea is if we were to actually plug x1 into our solution curve, it would be way up here. This right here, this is y of x1, okay? But we're not actually calculating that because we can't. We don't know what our solution is. What we're doing is we are using the value of y on the tangent line when x is equal to whatever x1 is. And so that value right there, that's y1, and it's equal to L of x1, okay? And so you notice there's a bit of a difference between these two values. We did not get the exact value, and we most likely never will unless the solution curve is a line. Most of our solution curves are not lines, so I would say most of the time we are not going to get an exact value. We're going to be off by some amount. Now this picture is kind of zoomed in, so I've made it look big, but technically this is zoomed in a lot, and x naught and x1 are very, very close to each other, maybe even close enough that we can't see it with the naked eye, okay? And so that would mean that that difference between the solution curve value and the tangent line value may also be rather small. I will say that Euler's method is an introductory method to approximation methods, and therefore it is not a good one. There are better methods out there, but we have to start somewhere. And some of the better methods are built upon what was learned from Euler's method. So we learn Euler's method, and then we learn other methods later on. And the other methods get better and better and better. All right, so that h value that I brought up before, it's called a time step or a step size. You'll hear both words to describe it. If h is very large, not very large, but just larger, then we will have fewer calculations, but we'll also get more error because we're taking bigger steps away from the original point that was actually on the solution curve. If we have smaller h values, right, so our x values are very, very, very close to each other, we'll get less error, but we will have a lot more calculations to do. So by identifying a new starting point, I maybe should have started with a new paragraph here, but let's say that, in this picture, we've got our approximation. We've got we've got our x1 and our y1. They're on the tangent line, but we have them. And they were found using this first form. Okay, so this first form, notice that to the right of the equal sign, we need knowledge of y naught, we need knowledge of x naught. Okay, so this uses x naught and y naught to find y1. Okay, and whatever you get for y1, it's going to pair up with the x1 that is in y of x1. Okay, once we have that, then we can move forward. Our goal is we're creeping towards some ultimate x value that we want to know what our solution is approximately equal to at that x value. So once we have x1 and y1 from the previous step, we can then calculate what y of x2 might be approximately. Y of x2 is approximately y2, and y2 requires knowledge of y1 and x1 in order to find y2. So this uses x1 and y1 to find y2. And once you get into that pattern, like the setup's not too bad. The calculations can be a bit tedious. You definitely want to use a calculator. But anyways, we would keep on in this manner until we finally get to the ultimate x value that we're after. Each step that we take, we're getting an approximation, and so we should hold on to as many decimal points as we can until we get to our final answer, okay? So the general form of Euler's method does not actually use like that L notation, the linearization function, but it is still the linearization function, okay? So up on top here, we have this written in a more straightforward form. So no L's, we just have, if we want to calculate y sub n plus 1, it will equal y sub n plus h times f of x sub n y sub n. And remember that f of x sub n y sub n, this is just your, I should write this as, this is your dy dx evaluated at x naught y naught. Okay? The other thing I want to point out in this is that y of n sub 1, that is actually approximately y of x sub n plus 1. Okay? Now, in order to find your x sub n values, you start at x naught and then you add repeatedly multiples of this h value. And we have to figure out, like, how many times do we do that? Like, when do we stop? And I think it'll be much more clear when we go through an example and do the calculations, but I'm just reading you what the formulas are right now. If we're told that we have some step size, maybe it's 0.5, and we know a start x value and an ending x value, but we don't know the number of steps we need to take to get there, we can calculate that. The number of steps is n, and it's equal to the x sub n, or the final x, minus the initial x, all divided by the h value, okay? And so that value of n will change depending on your step size, your h. We will be given x naught and y naught always, and we will be told to use Euler's method to approximate the solution at some x value, okay? And then when we use Euler's method to approximate solution, we saw in the previous slide that there's some error that shows up. And so we also have means to calculate what the relative error is, and that's just what is the error in relationship to the actual value, as well as the percentage relative error, okay? Now, notice that in the relative error and in the percentage relative error, there's an actual value in here. And so if we don't know what that actual value is, then we really can't actually find this, okay? And then the absolute error that's in the numerator of each of these fractions, that's taking the actual value minus the approximation, okay? So it's a bunch of stuff in here, but all of them, I should say, all of them require knowledge about the actual value. So we're going to work with differential equations that we could actually solve using the methods of the previous sections in Chapter 2. That way we could calculate relative error or percentage relative error and answer those questions. Not all questions are going to ask about relative error, but if they do, here are the formulas that you would use. Okay. Once we know what the relative error is, we can determine, or whoever needs the information that we're calculating it for, can determine whether the approximation is good enough or not good enough. Okay? Just once again, Euler's method is a basic introduction to numerical approximation solvers. And so it's not actually used in reality because it has a lot of error, but is the one method that we could maybe do by hand a couple of times. All the others are intense with calculations, and there's even more room for error just in doing those calculations if you try to do them by hand. Okay, so we're going to do 2 examples, and it's going to be a lot of writing, despite the fact it's just 2 examples. And so we're being asked to use Euler's method to obtain a 4-decimal approximation of the indicated value. First, use h is equal to 0.1, and then use h is equal to 0.05. One thing I want to note right here is that if we want to obtain a 4-decimal approximation of the indicated value, this means that we do not approximate throughout. We wait until the final calculation is made. The reason for this is that if you are to approximate, or were to approximate at every step, then you would be introducing even more error. So like the method is bad enough and introduces enough error, don't add to it, okay? And I'll show you what I mean by that, okay? So first we're given y prime is equal to xy plus the square root of y. We're also told y of 0 is equal to 1, and then we're just given this y of 0.3. So we need to identify what all of this is, okay? Y prime is equal to f of xy, okay? That is what we have to be very clear of right from the get-go. Y prime is a function of x and y. That's pretty clear. There's an x and a y in it on the right-hand side. And so if we want to define what f of x sub n, y sub n is equal to, we just go through that y prime expression and replace all the x's and y's with x sub n and y sub n. So I get x sub n, y sub n, plus the square root of y sub n. Okay, so that's the information I get from the differential equation. The y of 0 is equal to 1. This is telling me that x naught, y naught is equal to 0, 1. Okay, the y of 0.3, this is telling me my y of my final x value. Okay, so this tells me that right now what I know is I know that x naught equals 0 and x final equals 0.3. So I'm using information about my solution that I know when x is equal to 0 in order to approximate what might be happening with my solution when x is 0.3. Okay? So we have to calculate a few things before we can go forward. We're going to deal with the first case first. So h is equal to 0.1. And if that's true, then we need to calculate the number of steps we need to take. The number of steps n is equal to x final minus x naught over h. X final 0.3 minus x naught, which is 0, divided by 0.1, which is h. This simplifies to 3 steps. That means I should have 3 calculations. I cannot tell you how important this is. What I see in my experience is that many people will go too far in their calculations, or they'll stop 1 step early. So don't be that person. Just calculate the number of steps and then you'll know. Okay? All right. We know that y of 0 is equal to 1. Okay? The next x value that we're concerned about is 0.1 units away. Okay? So with h equal to 0.1, we'll know that x1 is equal to 0 plus 0.1, which is 0.1, and x2 is equal to x1 plus another 0.1, so that'll be 0.2, and x3 will equal 0.3, just add another 0.1. Okay, so those are the x values that we're concerned with, and notice that x3 equals 0.3. That is the final x value that we're concerned with. Okay, so now I want to go to, where is it? The top, y sub 1 first, but pay attention to this notation that I put to the left of my y sub n plus 1 because I use that a lot. So I'm just going to write this down again so that we have it. Y of x sub n plus 1 is going to be approximately y sub n plus 1, which is equal to y sub n plus h times f of x sub n, y sub n. Okay, let's do this. If we already know y of 0 is equal to 1, then we're going to be trying to calculate y of x1, which will be approximately y1, which should be equal to y naught plus h times, in parentheses, x naught y naught plus the square root of y naught. Okay, that's our form. Now, I wrote those in general terms. In other words, I have x's and y's in there. I didn't put numbers in. So let's see what else this means. x1 is 0.1, so that means I'm finding y of 0.1 is approximately y1, which is equal to y naught, and y naught was 1, plus h, which is 0.1, times x naught is 0, times y naught, which is 0.1, plus the square root of 0.1. Okay? And when I add this, multiply this, add this all together, I'm not going to do the basic arithmetic because what I do with this is I plug it into my calculator right away. I'm not going to try to do anything in my head. I just let my calculator do it. And so the value that I get right here is an exact value, and it's equal to 1.1. Okay, so what I just found right here was that x1, y1 is equal to, well, x1 was 0.1, and y1 is 1.1. If we were to go back to that image that I had up above, I just found this point, the x1, y1. Okay, so it's on the tangent line. It is not necessarily on the solution curve, but it's close. Okay, all right, the next thing, I should number these just to make it really clear. So we'll do 1. Okay, our second calculation, we want y of x2, which will be approximately y2, which is equal to y1 plus h times x1, y1 plus the square root of y1. And believe it or not, I actually do write these out every single time because it's too easy to just put numbers in, but accidentally put the wrong numbers in. Here I have a guideline. I know which x's, which y's I'm going to need, and I can pull them from the information up above, right? I've got my x1 here, I've got my x2 here, I've got my x3 here, so I can pull those values from up there. Directly above, I have the ordered pair that says x1, y1 is 0.1 and 1.1. And so those help guide me, okay? So y of x2, that's actually y of 0.2, And by plugging that in, I can see that this is not going to be my final step, right? Because it's not y of 0.3. Okay, so this is approximately y2, which is equal to y1, and y1 is 1.1, plus h, which is 0.1, times x1 is 0.1, times y1, which is 1.1, plus the square root of y1, which is 1.1. Okay. Again, I just plug this into my calculator and see what I get. My calculator gave me a lot of decimals, so the answer I got is not equal. It is approximately already. So it's 1.215880885. I keep every single decimal that my calculator shows me because it's not my job to approximate along the way. So the information that I got here was that x2, y2 is equal to this ordered pair of 0.2, comma, 1.215880885. Okay, so that was step 2. And step 3, I know I have 3 steps to take, so my numbering looks good. It's my last one. I'm finding y of x3, which will be approximately y3, which is equal to y2 plus h times x2, y2 plus the square root of y2. Okay, my calculator and your calculator probably also has this. There's like an option to enter the last thing that showed up as an answer. Everybody's calculator is different, but mine is such that if I do the second button and then my negative symbol button, I automatically enter whatever the last answer was. And so if my last answer was 1.215880885, I just do second answer to enter into my calculator. So you want to figure out what your calculator will do to help you, okay? So this calculation, when I plug everything in, I'm getting y of 0.3. Woohoo, we're going to be done. That's approximately y3, which is equal to y2 is this 1.215880885. I'm going to write it without all the decimals, but knowing that I'm going to plug in all the decimals, okay? So it's 1.21588, and it continues on, plus h, which is 0.1, times x2 is 0.2, times the y2, which is 1.21588, and that goes on, plus the square root of that, 1.21588, and that goes on. And then I let my calculator do the work, and what I get is approximately 1.350465492. Okay, now all that work, and the final answer is going to be in this box here, okay? Y of 0.3. That's what we were asked to approximate in the beginning. Y of 0.3 to 4 decimal places is approximately 1.3505, because next to the 4 is a 6, so we're going to round up. This is our final answer. A lot of work to get there, but that's it for the final answer. Okay? All right, the next problem is still in this problem. We have to go back up, and we were told to then use h equals 0.05. All right, let's do it. I kind of want to do a little bit of a copy paste here. I'm going to duplicate that and drag it down. Okay. Okay, so I have all the information that I need. My h now, though, is 0.05. So I need to recalculate the number of steps it's going to take. My x final is still the same. My x naught's the same. My y prime is the same. Everything else is the same. But if h changes, then the number of steps changes. So n is x final, which is 0.3, minus x naught, which is 0, all divided by 0.05. Okay, well, this is equal to 6. So I have 6 steps to take. That's a lot. Okay. Given that I know that I have 6 steps, though, and I know x naught is equal to 0, this means that x1 would be equal to 0.05. x2, we would add another h. It's equal to 0.1. x3 would equal the 0.15. That's just adding another h. x4, we'd add another h value to 0.2. x5, add another h, we get to 0.25. And finally, x6 would equal, adding another h, we get to 0.3. Okay, so we see our 6 steps. Where x naught we know, so that doesn't count as one of our steps, but we have x1, 2, 3, 4, 5, 6, and so we know we can't stop until we get there. Okay. This seems tedious, this row that I wrote, but trust me, when you get the right answer, it's not tedious. It's much more work to get the wrong answer and then try to figure out what went wrong. Okay, let's get started. So if we know that y of x naught is equal to y naught, then that means that y of x1 will be equal to y1, which is going to use y naught plus h times f of x naught y naught. So exact same setup as before, and this is step 1. Okay. We plug in x1 this time, and it's new. It's going to be y of 0.05. This is equal to our y1, which is written in terms of x naught and y naught. And so when we write it out, y naught is 1 plus h, which is 0.05, times our derivative function evaluated at x naught. Oh, you know what? I wanted to rewrite that up there. Instead of writing f of x naught y naught, I should write the actual function x naught times y naught plus the square root of y naught. Okay, now when I plug those in, I have 0 times 1 plus the square root of 1. Okay, this, when I plug it into my calculator, gives me exactly 1.05. So now I know that x1 comma y1 is equal to 0.05 comma 1.05. So that's good information to have, but it's not my final step. Step 2, y of x2 is equal to y2, which is, it's approximately y2. And up above, that was approximate as well. Okay, y2 is equal to y1 plus h times x1 times y1 plus the square root of y1. So we're going to plug in the values. x1 is 0.05 and y1 is 1.05. So this becomes let me write it down below. Y of x2, which is 0.1, is going to be approximately y2, and that's equal to 1.05 plus 0.05 times in quantity 0.05 times 1.05 plus the square root of 1.05. Plug that into my calculator, and I get, this is approximately 1.103859754. Okay, that's a big number, or a long number, I should say. Just as before, when I didn't write out all of the longer numbers in the next calculation, I'm going to do the same thing here for the sake of space and strengthen my hand left, but I will use the full-blown number in my calculations in my calculator, okay? So up here I can say x2, y2 is equal to 0.1, comma 1.103859754. All right, third step. Now we're looking at y of x3, which will be approximately y3, which is equal to y2 plus h times x2 times y2 plus the square root of y2. So we plug everything in. We are calculating y of 0.15, which is approximately y3. And now everywhere there's an x2 and a y2, we're going to plug in what we found in the previous step. Y2 we'll plug in as 1.1038 ... plus h, which is 0.05, times x2, which is 0.1, times our 1.1038 ... plus the square root of that, 1.1038 ... Close that. All right, plugging it into the calculator, I get that y of 0.15 is approximately 1.1619111418. Okay? And so then I can say that x3, y3 is equal to 0.15, comma 1.1619111418. Okay, so these are my steps along the way that I'm getting. They're just kind of my reference points so that when I do the next calculation, I can quickly see what the values are that I need. Step 4, we're looking at y of x4, which is approximately y4, which will be calculated in terms of x3 and y3. So we get y3 plus h times x3 times y3 plus the square root of y3. x4 is equal to 0.2, so we're getting closer to our final calculation. Y of 0.2 will be approximately the y4 value. That is equal to y3, which I will write as 1.1619 and then ... plus h, which is 0.05, times x3 was 0.15 times the y3, 1.1619 ... plus the square root of the 1.1619 ... Plugging that into my calculator, that gave me a pretty nice number. Still long though. 1.224521751. Okay. So now we have x4 and y4. x4 was 0.2, y4 was 1.224521751. Okay, highlight that again so I know where I'm going back to. All right, step 5. Okay, you have to be persistent with these. I will admit it gets tedious and long. I promise that on an exam you won't have 6 steps. I just need to know that you know the process, and doing 6 steps is going too far with it. Okay, y of x5, since we're on step 5, will approximate y5, which is equal to y4 plus h times x4, y4 plus the square root of y4. Let's plug those things in. x5 is 0.25. That's going to be approximately our y5, which is equal to, using the values we just calculated, y4 and x4. y4 is 1.2245 ... plus h, which is 0.05, times x4 is 0.2, y4 is 1.2245 ... plus the square root of that 1.2245 dot dot dot. My calculator tells me that this is approximately 1.292096024. Okay, and so now we have an x5 and a y5. x5 was 0.25 and y5 is 1.292096024. Okay, last step. Thank goodness there's a last one. 6. Now we're getting y of x6. That will be approximately y6, which is equal to y5 plus h times x5, y5 plus the square root of y5. Plugging everything in here, we've got y of 0.3, which is what we are after. This is going to be approximately the y6, which is equal to y5, and y5 was about 1.292 dot 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 plus h, which is 0.05, times the product of x5, 0.25, with y5, 1.292 dot dot dot, plus the square root of that 1.292 dot dot dot. And this gives me, in my calculator, 1.365082425. So finally, therefore, y of 0.3 is approximately, to 4 decimal places, 1.3651. And that's the thing we put a box around. Everything else was just the side work, really. But you have to show the side work, okay? That is part of the problem, showing that you know how to do this process, okay? All right, the next step. Oh, I should put in an aside. If you've done a few of the Euler's method problems in the homework, and you feel comfortable with the method, you feel comfortable that you're writing the proper notation as you go through your calculations, and that you could do like 4 or 5 steps in a problem on a test, then go ahead and do a search for an Euler's method calculator and use that to do like the formidable calculations, okay? I give you permission for that. All right, this next one, we're going to use Euler's method with h equals 0.1 to find an approximate value for the solution of the initial value problem at y of 0.5, then solve the differential equation and find the exact value, compare the approximation with the exact value by calculating the relative error and the percentage error. Now y prime plus 2y is equal to x cubed e to the minus 2x. That's our differential equation. And so that means that f of x sub n, y sub n will equal y prime, evaluated, sub n, which will equal x sub n cubed e to the minus 2x sub n minus 2y sub n. Okay? And then the information we're given is that x naught, y naught is equal to 0, 1. And we want to approximate y of 0.5. Okay? This 0.5, that's our x final. Okay, so we're told h is equal to 0.1. We need the number of steps we're going to take, n. N is x final minus x initial divided by h. X final is 0.5 minus x naught, which was 0, divided by h, which is 0.1. We have 5 steps to take. Okay? So let's see, we have x naught is equal to 0. Add h, we get x1 is 0.1. Add h, we get x2 is 0.2. Add h, we get x3 is 0.3. Do it again. x4 0.4, and finally x5 is equal to 0.5. Okay. All right, so we are going to go ahead and plug everything in. So I want to first get y. Sorry, this will be our first step. So 1. We have y of 0.1, which will be approximately the y of y sub 1, which is equal to y naught plus h times, it looks like we've got x naught cubed e to the negative 2 times x naught minus 2 times y naught. Okay, plug everything in. This is equal to 1 plus 0.1 times 0 cubed times e to the minus 2 times 0 minus 2 times 1. And so what this gives us is exactly 0.8. So right now we know that x1, y1 is equal to 0.1 comma 0.8. Okay, second step, y of 0.2 is approximately y2, and this will equal y1 plus h times x1 cubed e to the minus 2x1 minus 2y1. Plugging everything in, what we get is y1 was 0.8 plus 0.1 times x1 was 0.1 cubed e to the minus 2 times 0.1 minus 2 times 0.8. Again, it's messy, but I just plug it in, and I do always write it down. I would never just put this in my calculator and be like, bam, there's my answer, yay. You got to show your work. So show plugging it in, and then use your calculator. Okay, so what I get from my calculator is this is approximately 0.640081873. That's long. Okay. So this is my y2. Putting this together, I've got my x2, y2 is equal to 0.2, comma 0.640081873. All right. Step 3. Y of 0.3 is approximately my y3 value, which is going to use y2 plus h times x2 cubed e to the minus 2x2 minus 2y2. Plugging everything in, I'm going to do the same thing I did in the previous problem, where I do the dot, dot, dot on how long y2 is. So it's 0.64 dot, dot, dot plus h, which is 0.1, times x2, which is 0.2 cubed, e to the minus 2 times 0.2, and then minus 2 times the y2, which is 0.64 dot, dot, dot. And when I plug that into my calculator, that gives me about, where is it? 0.512601754. Okay, so that was x3 and y3. x3 was 0.3, whereas y3 was 0.512601754. Okay, a couple more steps, that's it. 4, we're calculating y of 0.4. It's approximately y4, which is equal to y3 plus h times x3 cubed e to the minus 2x3 minus 2y3. Plugging everything in, and I'll shorten up my y3 there, so it's 0.512 dot, dot, dot plus 0.1 times x3 is 0.3 cubit e to the minus 2 times 0.3 minus 2 times y3, which is 0.512 dot, dot, dot. And this gives me approximately 0.411563195. So then I know x4 and y4 are equal to 0.4, comma, 0.411563195. Okay, last step, 5. Y of 0.5 was what we were being asked for. It is approximately y5, which is equal to y4 plus h times x4 cubed e to the minus 2x4 minus 2y4. Okay, plugging everything in. This is equal to 0.411 dot, dot, dot plus 0.1 times x4 is 0.4 cubed e to the minus 2 times 0.4 minus 2 times the 0.411 dot, dot, dot. And this gives me approximately 0.3321262661. Okay, but we can simply say y of 0.5, and let's see, we weren't told any particular decimal place to round to. And so typically it's like we could say to, I don't know, 5 decimal places. I have exactly what my calculator gave me. But to 5 decimal places, y of 0.5 is approximately 0.33213. Okay? All right, that's not all we were asked for. That was just part 1. The second part says, solve the DE and find the exact value. Then compare the approximation with the exact value by calculating the relative error and percentage error. Okay, so we're going to solve this. Let me rewrite the differential equation. So we're going to solve. Let's see, let me write it out. Y prime plus 2y is equal to x cubed e to the minus 2x, comma, y of 0 is equal to 1. Okay, this is a linear equation, and it's already in standard form. Okay, so linear equation in standard form. So we're going to need an integrating factor, mu of x, which is equal to e raised to the integral of p of x dx. In our case, p is 2, so we get e to the integral of 2 dx, which is simply e to the 2x. So we multiply then mu of x to the dE. So we're doing all of our steps. We get e to the 2x y prime plus 2e to the 2x y is equal to, well, when I multiply an e to the 2x to x cubed e to the minus 2x, all the e's go away and we're left with x cubed. Okay. Now we're going to integrate, or we're going to solve, actually. It's not really an integration. So we're going to recognize that on the left-hand side we have d dx of e to the 2xy, and that's equal to x cubed. So now we can integrate both sides with respect to the same variable x. The integral of d dx of e to the 2xy dx will equal the integral of x cubed dx. Okay. On the left-hand side, the integral and the derivative undo each other and just leave behind the argument e to the 2xy. On the right-hand side, the antiderivative is 1/4 x to the 4th plus c. Finally, we solve for y. Y is equal to 1/4 x to the fourth e to the minus 2x plus c e to the minus 2x, where I've divided by e to the 2x and simultaneously rewritten it so that it's not in the denominator by giving it a negative exponent. Okay, now apply y of 0 equals 1 to find c. Okay, so if y is 1, we get 1 equals x is 0, so we get 0 in the first term, plus c e to the 0. This tells me c is equal to 1. So my final solution, y of x, is equal to 1/4 x to the fourth e to the minus 2x plus e to the minus 2x. Okay, but that wasn't all they asked us for. Let's go back and look. We're supposed to solve the DE and find the exact value at y of 0.5. Okay, so now we have the exact value. So y of 0.5 will equal 1/4 times 0.5 to the fourth power, e to the negative 2 times 0.5, plus e to the negative 2 times 0.5. Okay, and when I plug that into my calculator, it's an approximation that I get, but it's the closest approximation to this exact value. Okay, and so what I get is 0.373627557. And then just to recall, the approximate value was y5 is equal to, what do we get? 0.332126,261. So pretty close, accurate to the 10th place. Not great, but it's okay. So then we're asked to, what do they want? Compare the approximation with the exact value by calculating the relative error and the percentage error. Okay, so the relative error is equal to, it says absolute error in the numerator, but that's just the absolute value of the exact minus the approximation divided by the absolute value of the exact value. Okay, so we plug those in. In the top, we have the 0.373627557 minus the approximation of 0.3312126,261, all divided by the exact value, 0.373627557. And when I do that math out, I get an approximate number, of course, which is 0.111076646. Okay, that doesn't, that gives me relative error, but the percentage relative error gives me a little bit more information. It's not much different. So percentage relative error, is just equal to 100% times the relative error, which in our case will give us 11.11%. So that tells me right there a little bit more information. It says that our approximate value gives us an about 11% error. And depending on what you're building or working with, that might be okay, but it also could be deadly. So you want to be careful with error. That's all I've got for Euler's method. That was a lot of calculation, but not a whole lot of information. So really practice writing out all the things you need to use when calculating Euler's method. Get comfortable with it, but then also don't be afraid to use an Euler's method calculator once you are comfortable with the method. And as always, please reach out if you have questions.